Welcome to this new series where I will describe how we can use lenses to model dynamical systems. In this first video, I'll introduce what we'll be seeing in the series, and I'll tell you what a lens is and how we can think of a lens as a dynamical system. I learned about the material I will present from David Jasmeyer's book called Categorical Systems Theory, which is a work in progress. You can find the draft version of the book available for free on his website, which is davidjas.com, and I've also put the link in the description to this video. I'm extremely grateful for that resource, so if you find what I'm saying here interesting, you should go check it out. Okay, so let me now describe what we'll be talking about in this series. We will be looking at dynamical systems, which have some set of states, S, and these systems can take some inputs, A, and produce outputs, B. And generally, we'll draw these systems in form of these boxes like I've done here. Moreover, we'll be taking a compositional approach to building these dynamical systems, which means that we'll focus on how we can build larger systems from smaller parts. For instance, if we have a second system with states T, which takes inputs B and produces output C, we could think about running T in parallel with the system S. The idea here is that if we put these two systems in parallel, we can think of them as one big system. So I'm drawing a big box around both of them. And this big system will take pairs of inputs, one from A and one from B, and produce pairs of outputs, one from B and one from C. Another thing we'll be seeing is that if we have two systems in parallel, and we have some wires that have a matching type, which means they represent the same set, then we can wire these things together and produce a composite system. In this case, it's a system that takes an input A and produces an output C. So the idea here is that we give the system S some input A, it produces an output B based on that, and then we feed that output B back into the system T, which then produces some output C. Again, if we draw a big box around what's happening here in the internal part of this system, we can just think of this as an entire system that takes inputs A and produces output C, by forgetting about what's happening inside. So this describes the compositional approach to system building. We take some smaller, simple components that we understand well, and we put them together and maybe introduce some connections between them to produce a composite system. And the way this composite system behaves will be dictated by the simpler components that we understand. Now we'll see in this series that first of all, we can describe systems that take some input and use it to produce output. We can describe these using lenses. And moreover, we can also describe the wiring together of systems, again, using lenses. So all of the things I've talked about are things we can do when we model these dynamical systems with these objects called lenses. The reason I'm excited about this lens formalism is that it's extremely expressive. So if you want to do something with your systems, chances are it will be possible within this framework. With that out of the way, it's probably time we discussed what a lens is. A lens, the notation for which is this entire thing. So this lens is called F#F, and it goes between the pair of sets A minus A plus and the pair of sets B minus B plus. So this is just notation, but a lens consists of sets A minus, A plus, B minus, and B plus, along with two functions, namely a pass-forward map, which I'm calling F, that goes from the set A plus to B plus, and a pass-back map, which is called F#, that goes from A plus times B minus to A minus. Before explaining what exactly this structure is supposed to do, I would like to comment on the notation which I've taken from David Jasmeyer's book. We see here that in this part, so this is the name of the lens, we include both the names of the pass-back map, F#, and the pass-forward map, F. Next, in the second part, this is sort of like the part of a function where you describe what the domain and the codomains are. We see that here we've segregated these sets A minus and A plus into sort of a domain-like object and put B minus and B plus into a codomain-like object. And in between them there are two arrows. the top arrow goes from right to left, while the bottom arrow goes from left to right. These arrows here are supposed to remind us of the directions of the pass-forward and pass-back maps. So you see that here the pass-forward map is on the bottom, and this bottom arrow goes from left to right, and this is because the pass-forward map is a map taking an element from A plus and producing an element in B plus. So if you just focus on this bottom level here, this is just like the notation for a function between A plus and B plus. On the other hand, the passback map is a bit more complicated. What does it do? Well, it takes an element from A plus and also an element from B minus, and then uses that to produce an element in A minus. So in this way, the passback map is somehow kind of going from right to left, although it's not really as clear as with the pass-forward map. In any case, we'll see that this notation will prove to be quite useful when we do operations with lenses, such as lens composition and also putting lenses in parallel. Now, I'd like to tell you what a lens does, but this is kind of difficult because lenses are such a general structure and they can do a lot of things. So if you can't immediately imagine what this could be good for, it's probably best to just wait until we see some specific examples, and then you can maybe generalize from there. The most helpful thing I can probably say at the moment is that lenses provide a way of thinking about passing information between two different interfaces. So we will think of the pair A minus A plus as an inner interface and the pair B minus B plus as an outer interface. And the lens is somehow exchanging information between those. Let's draw this. So we have some inner interface, and this will correspond to this pair A minus A plus. And in this pair, we will think of the A minus as the inputs to the interface and A plus as the outputs to the interface. So this interface here has some inputs, A minus, and produces some outputs, A plus. On the other hand, we have this outer interface, B minus B plus, which we envision as surrounding the inner interface. So this interface has inputs B minus and outputs B plus. And we now envision this lens, F sharp F, as mediating between these two interfaces. How does this work? Well, on the one hand, we have this pass-forward map F, which maps from A plus to B plus. So we can think of this pass-forward map as taking outputs of the inner interface and producing from them outputs of the outer interface. So in our picture, F would be located somewhere here, and it takes the outputs from A plus and produces from it outputs of B plus. On the other hand, the pass-back map is more complicated. What does it do? Well, it takes some output from A plus along with an input from B minus and uses that to produce an input to A minus. So in our picture, F sharp would be located here. It takes some input from B minus along with some output from A plus and produces from that an input to A minus. So you see that instead of just directly converting B minus inputs into A minus inputs, it also takes into account what the current output of A plus is. So this allows for some greater flexibility when processing inputs to the inner interface. Okay, so that's one way to think about what a lens is, but as I promised before, all of this will become a lot more concrete when we move on, and specifically when we see how to think of dynamical systems as lenses. That brings me to the next definition, which is that of the specific type of dynamical system we'll be considering here. These systems are called A-B Moore machines, and they consist of the following data. So we have some set of states, S, we have a set of inputs, A, and a set of outputs. And now we need a way to encode the dynamics for this system. So first of all, we have an output function, which I'll just call out, which takes a state and produces an output. And finally, we have an update function, which I'll just call up, which takes the current state along with an input and uses that to produce a new state. Pictorially, we can draw an A-B Moore machine as a box. So I'll put S here to indicate its set of states. Then I'll draw a box around it. And finally, I'll put the input set here in a wire going into the system and the output set here in a wire going out of the system. Now the output function, what does it do? It takes some state of the system and produces an output. So in our picture, the output function would take a state from S and then use that to produce an output in B. On the other hand, the update function takes the current state of the system along with an input and produces a new state. I'll draw the update function here. What does it do? It takes a current state from S along with an input from A and produces from that a new state in S. So in summary, we can think of an A-B Moore machine as a discrete time system which can do two things. First, we can update the state based on a given input. And second, whenever we want, we can always read out an output based on the current state. Now, often we'll think about these things as happening sort of one after the other. That will always update the system once and then read out the output, then update it again and then read out the output, and so on. At this point, it's probably helpful to see an example. So let's do an easy one. So let's model a counter. So we can think of maybe one of these, I don't know if you've seen these before, these little clicker things which people have when they count like people entering the movie theater or something like that, where you can press on this button and then it will update the number here by 1. So this counter will have some starting number and then you click once and then the number will increase by 1. You click again, it'll increase by 1 again, and so on. Now for simplicity, we'll just assume that this counter has an infinite capacity to count numbers and that the only thing we can do is just press this button and it will increase the count by 1. So in this case, our set of states for the counter will be the natural numbers because we just want to be able to count things. Next, our input set will just consist of a single element, which I'll call press, which just allows us to press the counter. We can't do anything else besides pressing it. We can either press it or not. So our inputs will just be this single signal press. And finally, we need to define our outputs. And again, our outputs will be the natural numbers because the outputs are the number we're displaying on the counter. Now that we've decided on our set of states, inputs, and outputs, we need to define our output and update functions. So let's start with the output function, out. This is a function going from the set of states to the set of outputs, which in our case will be a function from the naturals to the naturals. Now we're thinking about our set of states as being the current count as tracked by the counter. And on the other hand, we're thinking of the outputs as being the number that the counter is currently displaying, which should also just be the current count. So this means that our output function should take the current count, thought of as a state, and just display it. So it'll map some natural number n just to the same natural number n. Therefore, our output function is in fact just the identity in this simple case. Okay, let's next turn to the update function. So the update function up goes from the set of states cross our inputs to the set of states. So in our case, this will be a function from the natural numbers cross this singleton set which contains the element press to the natural numbers. Now the update function will model the dynamics of our system. So what does it do? Well, we take some natural number n along with this element in the singleton set press, and we map it to n plus 1. So this is saying that if we're in a current state n, so the current count is n, and we have this input press, then we increment the current count by 1. So we can now think of our system running. So we have some current count, which is a natural number, and then we press the button, and then the count gets incremented by 1. And at each step, we can read out the state by just using this output function, and it'll just read out the current count. So this was a really simple example for multiple reasons. The first of which is that we only had a single element in our input set. So there's really only one thing this system can do. One way we could maybe improve the fidelity of this model is by including something like a reset button. So this would be a counter which has two buttons, one of which is the thing you use to increment the count, and the other one is the button you use to set the counter back to 0. So in this case, we would include an extra element called reset in the input set. And now we also have to change our update function, because the update function depends on what type of input you feed it. So in this case, we'd also have this element reset in the domain of this update function. So we have to additionally specify what happens when we have the input reset. So I'll just do this by differentiating two cases. So in the case where we have input press, we will increment the count by 1 as before. But in the case where we have reset, we just map to the number 0. So regardless what the count is currently, if you press the reset button, the count will be reduced back to 0. So this would be one way of increasing the complexity of this system. Now, another thing that made this original system particularly simple was that the output function here was just the identity function. So in a more general system, we might have outputs that differ from the current system state, and the outputs might not surface the entire state of the system. So let's again add to this current example. Suppose that instead of having a counter which displays the current count, the counter only displays whether the current count is even or odd. So this would amount to having an output set, which is the set n mod 2n. So this just has two numbers, 0 and 1, where 0 represents the even numbers and 1 represents the odd numbers. Now again, we have to modify, in this case, our output function so that it has, again, the proper codomain. And the natural thing to do here is just to map a natural number to its equivalence class mod 2. So I'll just denote this n bar. So specifically what it'll do is it'll take a natural number, and if it's even, it will map it to 0 in n mod 2n, and if it's odd, it will map it to 1. So in this system, which I've modified in pink, the counter no longer displays the current count, it only displays whether the count is even or odd. And so this gives an example where the internal states of a system could be more complicated than what is surfaced in its output. So I hope you're beginning to see why thinking about these systems is really cool, because you can just kind of come up with some example on the fly, and then you can modify it a bit and just kind of include whatever you want. Okay, so far I've told you what a lens is, and then I switched gears and told you what an A/B Moore machine is. And if you are kind of observant, you'll notice that some of these things look very similar to what we saw previously in the definition of lenses. So this output function here kind of looks like the pass-forward map, and this thing here looks kind of like the pass-back map. However, in the case of the A/B Moore machine, we don't have 4 sets like in the case where we were looking at the lens definition, but rather just 3. However, it turns out that these A/B Moore machines are just special cases of lenses, and that's what we'll see next. So I hesitate to even call this a lemma, but I've written it down like this so we can have a small proof. So it states that an A/B Moore machine is just a lens of the following special type, namely a lens that has in its domain 2 times the same set S, which are the set of states, and in its codomain it has the input and output sets A and B. And moreover, the 2 functions we need to define for the lens will be the update function and the output function of the corresponding A/B Moore machine. So let's elaborate on why this is the case. So first, we suppose that we're given a lens of the above type. So we just need to remember what the objects were that were involved in such a lens. So having such a lens means we have sets S, A, and B. So then we have sets S, A, and B, along with two maps, namely this map called up and the map called out. And this map called up is the pass back map, while the map called out is the pass forward map. So the pass forward map in our case is called out, and by the definition of a lens, this map goes from S to B. So remember that the pass forward map is just like a function if you limit yourself to this bottom tier of the notation. So it takes an element of S and produces an element of B. On the other hand, we have this pass back map. In our case, this is suggestively called up. And what does the pass back map do? Well, it takes an element of this bottom part of the first interface and an element of the top part of the second interface and produces an element of the top part of the first interface. So this will be a function from S cross A to S. Okay, so if we're given a lens of this type, it means that we've specified sets S, A, and B along with two maps, namely one called out from S to B and another called up from S cross A to S, and this is precisely the data we need to define an AB Moore machine. So this is just an AB Moore machine. Now, conversely, if we're given some AB Moore machine, then we have the data necessary to specify a lens of this type. Why is this? Well, again, an AB Moore machine, we can just kind of use this above part of the proof, consists of these three sets along with these two maps, and we've seen that that's exactly what we need to specify a lens of this type. Therefore, if we're given an AB Moore machine, then we have all the data to specify a lens of the above type. Okay, and so this concludes the proof. Well, essentially we've just seen that in both cases, if we think of an AB Moore machine or a lens of this specific type, then we just need exactly the same data, so those two things are basically the same. Now in what follows, we'll basically forget about these AB Moore machines and just focus on lenses of this specific type as representing the dynamical systems we want to think about. So just to make sure this correspondence is clear, I'll repeat the example with the counter we had before, so without introducing any of the fancy stuff we had in the end, in terms of lenses. So recall that the counter had states, the natural numbers, had input set, which consisted of this singleton with the element press, and outputs, the natural numbers. Moreover, we had an output function called out going from the naturals to itself. This was just the identity, so it mapped each natural number to itself. And next we also had the update function up, which goes from the set of states, so the natural numbers, times the input set, which in our case is this singleton, and produces a new state which lives in the natural numbers. What does the update function do? Well, it takes a natural number n along with this only element in the set press and increments the count by 1, so maps it to n plus 1. All right, so that's the data we had for our AB Moore machine. And now how do we represent this as a lens? So as a lens, well, we just write it as, so we have to specify what the pass forward and pass back maps are, and also what the domain and codomain interfaces are. So in our case, the domain interface will just consist of this set, which is the set of states. So maybe I'll write it in a general form again, the thing we saw in the lemma. So we have the set of states appearing there. And then we have the inputs appearing in the codomain interface on the top and the outputs appearing on the bottom. And then here for the functions, our pass forward map will be the output function and our pass back map will be the update function. So this is the general notation we saw in that lemma, and in our specific case, well, the update and output functions, they have the same name, but our set of states is the natural numbers, while our set of inputs is the singleton containing the element press, and our outputs are the natural numbers. So from now on, I'll be writing these AB Moore machines in this format here. And so if you see something like this, where these two sets are the same, and I've called the pass forward and pass back maps up and out, then you should be thinking that this will represent some type of dynamical system. Okay, so instead of presenting you with more examples, which would be quite easy to come up with, I just encourage you to think of your own examples and try writing them down in terms of an AB Moore machine and also in terms of a lens. At the moment, it might still be unclear why we're using lenses at all, because it seems like a more complicated way to describe what we could more easily describe just as an AB Moore machine. However, we'll see that using general lenses, so lenses that don't just have this specific form, will allow us to do additional things we can't do with the AB Moore machines. For example, we'll see that we can use general lenses to wire different systems together. Doing so will involve, first, putting two systems described in terms of lenses in parallel, and second, composing these parallel systems with an additional lens that describes the wiring pattern between them. Hence, to build more complicated systems out of simpler parts, we'll need operations we can perform on these lenses. And that's what we'll start describing in the next video when we'll look at lens composition.